Now it's time to discuss the internal elements of our setup in detail. Our main focus is service function chaining. The idea is that a client will access a service with several CNFs in between. For different services, the number of CNFs will vary. So it might be just one CNF, but it could be also 4 CNFs if needed. Now let's take a look at what services and what CNFs make up our setup. Since we wanted to differentiate the services according to the transport protocols they use, we have 2 UDP-based and 2 TCP-based services. The first service is the TFTP server, which allows the client to download files, for example. And that's what we do in our setup. The second service that uses UDP is an NTP server, which is marked as service 3. On the other hand, the TCP-based services are service 2 and 4. They both act as HTTP servers. Finally, the last service is access to the internet. There are 5 CNFs in our setup: flow classifier, firewall, NAT, load balancer, and external gateway. Now let's look at how it all works together. We start with the client connected to the flow classifier. This CNF classifies the traffic flows coming from the client and decides where they should be forwarded. The flow classifier is a key element of our setup as it is part of every service chain we create. Next, we'll launch the service 1 instance and we connect it directly to the flow classifier. After the client, the flow classifier and service 1 have been properly configured, the client can now access service 1. Now let's see how internet access will be provided. Internet traffic requests coming from the client are processed by the following chain of CNFs: the flow classifier, the NAT, then firewall, and the external gateway. Next, we look at service 2. This time we would like to provide additional firewalling for traffic between the client and that service. Now let's look at how the client can access service 3. This is done similarly to service 1, but now, since we have the NTP server here, we wanted to be able to synchronize time with servers available on the internet. Therefore, the service 3 instance will also be connected directly to the NAT. And the last service in our setup is service 4. 3 instances of the service will be deployed in total. Therefore, we need the load balancer CNF on the path between the client and service 4. And this completes our setup from the data plane perspective. Our PoC runs under Kubernetes. It's up to you how you deploy the Kubernetes cluster. We used a solution named Kind, which is a very useful tool for running local Kubernetes nodes as Docker containers. On top of the Kubernetes cluster, we installed the network service mesh system. We use an NSM to create all the links between CNFs, service instances, and the client you saw in the previous slide. It is worth mentioning that we used an NSM version equal to 0.2.0. Here's what it looks like. We have a 3-node Kubernetes cluster. We install the NSM on it, and then add Kubernetes pods one by one, which form the data plane of our setup.
Now, let's take a closer look at the CNFs we implement in our setup. They are all based on an open source vpp-agent solution from the Ligato project. This vpp-agent is composed of plugins that communicate with the underlying VPP and kernel network mechanism. In terms of configuration, it also has plugins that allow communication with external applications. It also includes CLI utilities. Let's see how to configure a CNF based on vpp-agent. To do this, we will use 2 plugins. First, the REST plugin, and then the etcd plugin. We'll take a very simple example. Let's assume that we want to configure a new interface for the VPP. Here, how you can do it using REST. Then we will create a new bridge domain and assign that interface to it. To do this, we will establish a connection to an external etcd instance that stores the requested configuration. The Ligato project provides a dedicated CLI tool called Agent Cattle. The Agent Cattle tool lets you manage and interact with different vpp-agent internal components. This includes checking their status, making a running configuration dump, configuring logs, and so on. Another available tool is vpp-cattle. This is a standard CLI from the FDAO project and only allows interaction with VPP. The CNFs we use in our setup are not vanilla implementation of the Ligato VPP agent. They are based on another open source solution called Universal CNF from the NSM project. What is UCNF then? Well, it is a Ligato VPP agent enhanced with a native ability to interact with the NSM system. This is done by adding appropriate implementation to the original VPP agent. UCNF has three main functional components. Its data plane is primarily VPP from the FDAO project. Next, we have the Ligato VPP agent. And finally, we have a binary named CNF VPP agent. It is all delivered together as a Docker image. The additional CNF VPP agent component is written in Golang. This implementation provides the mechanism for an abstract CNF to natively interact with the NSM system, and also to get configuration from its data plane. This also includes specific implementations for Ligato VPP as a backend. How does it work in practice? To configure the UCNF, you need to prepare a configuration file with a dedicated semantics. The config file is parsed by CNF VPP binary. It talks to VPP agent, which eventually configures the VPP data plane accordingly. Now, let's analyze the example config. Let's start with the fields related to the interactions with the NSM. To connect our CNF to one or more network service endpoints, we need to specify each such request within a separate client field. Now, when we want our CNF to act as the network service endpoint for various network services, we need to add a new item to the endpoints list in the configuration file. Each item is a different service. Please note that we are also responsible for specifying an IP prefix pool used by the network service clients that request a given network service from our CNF, since it announces the service. This is in fact an indication of the network subnet, which is then broken down into smaller 30-bit mask subnets to handle incoming connection requests from different clients. The configuration file may also include CNF data plane configuration. It is specified within the dp-config field, as you can see. The example shown in the slide is for configuring a new access list on the VPP. Now let's look at the UCNF Dockerfile to see how it is built. As you can see, this is a multi-stage build. During the build stage, the CNF VPP agent binary is built based on its Golang source code. The runtime stage is performed on the image marked as VPP agent. Here we assume some version of the Ligato VPP agent will be used. The binary built in the previous stage is copied here. Moreover, the original VPP agent configuration is slightly changed. First, the configuration file for connecting to etcd is removed. Why? Probably because since the CNF data plane config can be passed within the dedicated file we just discussed, there is no need to use etcd for this purpose. Additionally, the telemetry plugin is disabled. And the same is done with the kernel networking plugin. When the UCNF image is ready, we can refer to it when we want to deploy the UCNF in the Kubernetes cluster. We provide a dedicated configuration file as a config map. The file used in the example you see on the slide contains both definition of the interfaces to be created by the NSM system, as well as the CNF data plane configuration.
We'll come back to the UCNF in a moment, but now let's consider how the CNF or any other network element works in general. Imagine that we have two CNFs deployed somewhere. They are connected to each other. Over time, a number of different traffic flows enter CNF1 to be then processed and forwarded to CNF2 for further processing. To make this possible, both CNFs must be properly configured. Now imagine that another CNF has started up and some other flows have emerged to be processed by it and then forwarded to CNF2. Again, to handle these flows, we need to configure the third CNF and update the configuration on CNF2. In general, whenever there are new flows to be processed, one or more CNFs must have their config updated. The main conclusion from this example is that in real-world scenarios where CNFs are used, their configuration changes over time. Moreover, it happens many times. Now we ask ourselves, how does this relate to the UCNF use case, where the approach to configuration seems to be different? As we saw earlier, the configuration of the UCNF is assumed to be static. It is passed in a config map and then injected into the UCNF instance as soon as it is started up. So how to update the config for a given UCNF? Well, all we can do is destroy the oldest instance and run another one with the updated configuration. But here comes another problem: how to ensure service continuity. Here the use of a Kubernetes rolling update strategy can theoretically help, however, not in all cases. We can end up with a lot of redundant connections within the NSM, general instability, and still have unresolved service continuity problems. Another problem is how to manage a set of different configurations for a given UCNF. Storing them in multiple Kubernetes manifest files seems to be inefficient and inconvenient. So as you can see, the UCNF in its original form is not very suitable for use cases where we deal with high network dynamics, both in terms of network topology and traffic loads to be served. This implementation is only relevant to simple static cases. Therefore, we decided to slightly customize the UCNF to make it suitable for use in our setup. First, unlike the original UCNF, we rely on communication with an external etcd to get the configuration for the CNF data plane. This applies to all of our CNFs. We run each CNF with zero config. The only thing specified in the configuration file are the connections to be made by the NSM system. Each configuration change that appears in the etcd is downloaded by the CNF to which it is addressed. This operation can be repeated many times in the lifecycle of each CNF. Thanks to such an approach, we can avoid the problems that we identified and discussed earlier. We only use one etcd entity in our setup. The configurations addressed for individual CNFs are distinguished by the so-called microservice label, whose value is set in the Kubernetes manifest file for each CNF deployment. Also, we re-enabled the telemetry plugin for each CNF because we want to provide observability in our setup for all CNFs. We do this using Prometheus, which gets various types of metrics provided by the CNFs. Then they can be visualized in Grafana. Another change concerns NAT functionality. One of the plugins provided by the Ligato vpp-agent is the NAT plugin. We noticed that the current implementation of this plugin limits the ability to perform NAT static mapping for IPv4 to DNAT mode only. This is de facto somewhat artificial limitation, as the underlying network mechanism the VPP agent operates on, which is VPP, enables NAT static mapping without distinguishing between DNAT and SNAT. And this situation was a problem for us because for one of the service chains in our setup, we needed to do static mapping in the SNAT mode. Therefore, we modified the NAT plugin source code to get rid of this limitation, and then we built our custom VPP-agent image. A final remark is that NAT static mapping on VPP only works in the so-called endpoint-dependent mode. Therefore, the following line has to be added to the VPP startup config file. Also, we re-enabled the Linux plugins. This is necessary because in one of our CNFs, we need to configure the connection to the outside world. This goes beyond the VPP. We also need to configure some mechanism within kernel networking to accomplish that. The VPP agent can supervise the completion of this configuration. It can control both underlying VPP and kernel networking entities, but to make it possible, Linux plugins must be enabled. Okay, so far we've talked about the Ligato VPP agent, the UCNF, and the changes we made for our setup. So let's try to put it all together to better understand what is what. The base for the target CNF we use in our setup is a vanilla VPP agent from the Ligato project. By adding the Golang code that enables native interaction with the NSM, and then by changing the VPP agent configuration, it becomes the so-called UCNF. And this implementation is provided by the NSM project. Then, by modifying the source code of the Ligato VPP agent and its further reconfiguration, we receive the target version of the UCNF, which we use in our setup.
Okay, now let's go back to the topology that is going to be built in our setup. As you remember, it is made up of CNF, service instances, and a client instance. However, in order to make it possible for the NSM to create all the connections between them, we need to define them in advance. For this purpose, we prepare an appropriate network service manifest. First, we need to define the name of the network service. We use only one network service in our setup, but if we wanted to have more, we would have to create a separate manifest file for each of them. It is also possible to define the so-called matches. This allows you to specify exactly which endpoints the client should be connected to. They are all identified using labels. Now, let's look at a simple example. Within each element of the list called matches, we define the source selector and the destination selector, which indicate the labels that correspond to the network service client and network service endpoint respectively, between which a virtual wire is to be established. In our case, the vWire will be established between the NAT and the flow classifier because the labels we see here are defined in the manifest file of these CNFs. And here is another example. It shows how you can create connections to more than one endpoint from a given client. What you need to do is simply define more than one destination within the root list. The examples we've discussed so far are about creating links between CNFs. From the NSM system perspective, our CNFs can act as both clients and endpoints. This native ability to interact with the NSM system is implemented directly in the CNFs. As we know, the CNF VPP agent component is responsible for that. But we also have other objects in our setup, such as services and client instances. They are assumed to work as network service clients only. What is important, unlike CNFs, they are not NSM aware. So how they can interact with the NSM system? This can be ensured by injecting a dedicated NSM init container into their pods, which provides the functionality of a network service client. How can this be declared in Kubernetes? A special annotation must be added within the manifest file. The field value must contain at least the name of the network service. If you want to create a link to a specific endpoint, you can also put the name of the particular label. Of course, the corresponding match has to be defined in the matches list for this network service. If you want the NSM to create more than one connection for your pod, enter another network service name with an optional label after a comma, as shown in this example. Now, let's look at how our CNFs can communicate with the etcd. We have created a Kubernetes service for the etcd instance. The CNFs we use can access it as they have the appropriate name and port number stored in the dedicated etcd configuration file. This applies for all CNFs we use in our setup. How is communication between the CNFs and Prometheus ensured? It's also based on Kubernetes service. We create an individual service for each CNF. Prometheus in turn is launched with a certain configuration. It is passed as a config map. It contains a list of targets the Prometheus instance is trying to connect to. In our case, these targets are the CNFs. Each of them is reachable by the name of its Kubernetes service and port number. Also, the Prometheus instance has its Kubernetes service created in our setup. It is consumed by the Grafana instance, which takes the data for the visualization from Prometheus. To make it work, one has to put the Prometheus service name and the port number in the Grafana web UI.